So, good morning once again, and now we are going to discuss our Viterbi algorithm approach, how we can use it to perform equalization. So we are not really going to calculate this equalizer. This is some more or less universal method that can be applied not only to equalizers, but also, for example, to error correction codes, of which we will talk later at the conclusion of this course, and different applications as well. In our particular case, we are going to actually use this algorithm to perform detection of symbols. So if you remember, here in the practical exercise number 5, yes, for example, in this method, we did calculate this equalizer. Here, for example, we have calculated equalizer with autocorrelation method. Then we used this equalizer. Yes, and after that, we have wait a minute. No. First, we did where here we did use detector. No, that's correct. First of all, we calculated this equalizer. I was just didn't scroll enough and was surprised that I didn't see this line. So we first calculated the equalizer, then we used this equalizer, then we detected the symbols. Yes, so we used some detector with a simple method of rounding the values here, and basically then compare the results. So Viterbi detector is actually a detector itself. So in that case, if we use Viterbi algorithm here, we no longer need this line because Viterbi will automatically find this solution for us as well. So it is a detector that can be used as a demodulator. And at the same time, it also works as equalizer that since it is trained for some particular impulse response. So this Viterbi detector will be for specific impulse response just the same way as any equalizer. So there are different types of nonlinear equalizers, and we'll speak of that in next week more, what kind of alternatives to this Viterbi detector can be used. But this method is one of the how to say, practically robust and reliable. So we start with the Viterbi detector equalizer. First of all, let me remind you that we can represent our channel as a filter, yes, with impulse response coefficient. So for example, let us take simple filter, a simple channel with one reflected path. So we have direct path, and this direct path is 100% energy is saved. Yes, so basically all the energy we have transmitted is received. Of course, this is somewhat idealistic situation, but for understanding the operation of Viterbi algorithm, this will be good enough. Yes, and you can consider that during the reflection of from the subsurface, the second signal has lost half of its energy, and basically what we have received is only twice a smaller signal because of this reflection effect. Yes, so we can say that this impulse response has in total two values. Yes, so this is the length of the impulse response, so the effect of memory for our channel, and accordingly the values of these filter coefficients are, here we have 1 and here we have 0.5. This is finite impulse response filter, filter. Yes, accordingly, once we send here 1, the first value is going to be 1, and the second value is going to be 0.5, followed with zeros, of course. 0, 0, 0, 0, 0, 0. So we are going to have 0, 0, 0, 1, 0.5, and then 0, 0, 0. So that's impulse response of our filter, yes. And this is how exactly our channel works. So what we are going to do now is to actually find all the possible combinations of how this symbol can be calculated. So you can consider that our input data consists of plus minus 1 and plus minus 3, for example, if we are talking about quadrature amplitude modulation 16. Yes. However, for simplicity, we are going to assume that we only use pulse amplitude modulation, PAM2, in this particular case. So our input data is limited with plus 1 and minus 1. And it can work with plus minus 3 as well for quadrature amplitude modulation. And we are going to try this next week in our practical exercise when we will write a simulation program for channel. And basically, you'll see that it also works for quadrature amplitude modulation. And when it will be relevant, I will make remarks about this, what will be different in these states and Trellis diagrams we will discuss. But for now, let us consider that input data can be plus 1 or minus 1. And accordingly, we can say that for these two symbols, so obviously the result yk depends on two symbols in draw, yes, so we can write multiple combinations. We can transmit plus 1 and plus 1. We can transmit plus 1, minus 1, minus 1, plus 1, and minus 1, minus 1. So we only care about last two symbols here. Yes, if the impulse response has three values, 1, 0.5, 0.5, for example, then we should care about three symbols, and we need to consider plus 1, plus 1, plus 1, up to minus 1, minus 1, minus 1. That would be in total 8 states. Yes, so each of these possible transitions is called a state. Yes, and there is a finite number of such states. In this particular case, this is 2 power of v. Yes, state. And yes, and accordingly, yes, I will mention why we have minus 1 here. Yes, so this is the number of total transitions. Yes, and the number of states from which we go. You can see clearly here that it's repeats itself. Yes, so basically the number of unique states is actually twice as smaller. Yes, 2 minus v divided by 2, which is exactly the same as 2 power of nu minus 1. So this is actually a Greek letter nu. Yes, and accordingly, this is why here we have this number of states. And this number is finite number. Yes, so that's why we call this a finite state automata. Yes, so the channel is this finite state automata. So we are going to calculate all the possible transitions, as I said, considering that the currently transmitted symbol is AK and the previous symbol is AK minus 1. And the actual channel output symbol is YK. So this works like this. So consider we have this channel. Yes, channel. Then we have input symbols, AK. We had previously AK minus 1. We had previously AK minus 2, and so forth. And we have accordingly output symbols, YK, and so forth. So this YK will depend on these two last symbols. Yes, and here we are just making a table of all the possible states. Yes, and transitions, and accordingly calculate what is the actual value. So the output value can be calculated in accordance with this formula in general case. Yes, this is actually convolution formula for filters, which I have also mentioned in the practical exercise today already. Yes, exactly the same formula. Here as data, we have the input values of the channel, and as impulse response, this is the characteristic of the channel, which we need to know. Yes, and the result is output data. Yes, so basically in this particular case, once we have nu equal to 2, our sum is going to consist only of two values. Yes, so that's going to be AK minus 0 multiplied with H0 plus AK minus 1 multiplied with H1. Yes, in our particular case, H0 is 1 and H1 is 0.5. So this is the formula for our case, for our channel, which we use here and substitute accordingly AK into this position and AK minus 1 into this position. Yes, so here you can clearly see that we calculate actual value. So H0 is 1 and H1 is 0.5. So we have calculated all the possible outputs of our channel, and that means that if we send symbol +1 currently at this moment, and previous symbol was also +1, then the output is going to be 1.5. If the previous symbol, however, was -1, the output is going to be 0.5. Yes, and here we can plot all these stats, all this in the form of graph of states, as this diagram, which is very important for the operation of this Viterbi algorithm. Accordingly, I will show you next lecture today in our practical part how to solve this for your specific parameters. Yes, so this is simple case that we care about the previous state and the new state. Yes, so basically each of them can be either +1 or -1. In this particular case, only one previous symbol matters, and we only have two possible values for this previous symbol, +1 or -1. If what we transmit right now is +1, then we are going to transition into a new state, which is also +1. So consider that we have this data, +1, +1, +1, let's say -1, -1, +1, and so forth. And our currently transmitted symbol is this one. So it goes from the state of the previous symbol, which was +1, and for the next step, if we consider the next symbol, what was our previous symbol state is now a new state. So basically we go from this state to this state. Yes. Now, if we consider this symbol, again, we go from +1 to +1. Next symbol is going to transition into -1 state. Yes. And we mark this with these lines. So for this particular case, if we have +1 previous symbol and +1 current symbol, so this is currently transmitted symbol, we transition with this line to the new state, which is also +1. And in the process, we send according value, which is 1.5. Yes, so we transition from state +1 to state +1 with sending value 1.5. So that's for transition of +1. If we, from this same state, send value -1, so this is AK is -1, and our original state is +1, then we transition to new state -1, because this is going to be next state for the next symbol, and accordingly, we end up in the second state, which is -1. And in transition, during this transmission, we send -0.5 value. Yes, the same way goes for working with from the state -1. If we from -1 send from, so this is our previous state. Yes, send value -1. Then we transition to state -1 and send value 1.5. Yes, -1.5. And if we send +1, sorry, here, we go into state +1 and basically during the process send value 0.5. So this diagram describes all the possible transmission cases depending on previous state. And accordingly, it also shows on these lines what actual signal channel output values are received during the process. Yes. So what will be different if we consider states +1, +3, -1, and so forth. So in that case, we are going to have in total 4 possible states. So let's say +3, +1, -1, and -3. And we are going to have 4 possible transitions because we can send any combinations of +1 and -1. So in this particular case, for example, from state +3, we can go into state +3, we can go into state +1, we can go into state -1, and we can go into state -3. Yes, and the same will work for any other. So here we are going to have these transitions. Next, we are going to have these transitions, and so forth, right? And for each of these transitions, we will have specific value that we can calculate, for example, in the form of this table. We will also write a program that will help us with this graph drawing during the practical part today. So, and this diagram shows actually how this signal is transmitted. However, what matters much more is how we are going to understand from this value that what we wanted to receive was actually -1. Well, in this particular case, you can clearly see that there is no case that we can mistake if we take only sign. So, for example, if we take -1 as a received symbol, then we only observe what sign is of our data. So here we have plus, here we have minus, and this accordingly matches. However, this will not always be like this. For some impulse responses, this can be misleading and incorrect. Yes, well, we'll see in practical part today if that will be the case, but at any rate, this can be, well, difficult. Yes, in your practical exercise, however, we are going to have today 3 symbols, AK, AK -1, and AK -2. Yes, so basically +1, +1, +1, -1, +1, +1, and so forth. So our state then is going to be represented by last 2 symbols. And in total, we are going to have 4 such states. Yes, +1, +1, +1, -1, -1, +1, and -1, -1. And there can be only 2 transitions in each case, yes, from each state. So we can send either +1. So in that case, we are going to transition to a new state, which will be +1, +1, yes, like this. And we can also send -1, and we are going to transition into a new state, which is -1, +1 here. Yes, no other possible transitions are valid. Yes, so this transition is invalid. It cannot happen. Yes, and similarly, such transition also cannot happen because we cannot send some symbol and end up in the state when this previous symbol, wait a minute, this one, will be replaced with -1. It cannot change. So this symbol is already fixed as a +1, and as a fact, we will always end up either in this state or in this state, because it depends on this symbol, which will be shifted by 1 position, right? Which is already +1. So we, in no way, it cannot change to -1. So it's impossible to be changed. We'll talk about this a little bit more in our practical part today, but for now, I just wanted to point out that this is exactly what makes this Viterbi algorithm working, knowing the fact that not all transitions are valid in this trellis, yes, in this state diagram. There are only few of the valid transitions. Similarly, if we take +-3 and +-1 and take, for example, a number of states also 3, yes, AK, AK -1, and AK -2. So for example, +3, +3, +3, then -3, +3, +3, -1, +3, +3, and so forth. So in that case, we are going to end up with 16 possible states. So the number of states is, as it was mentioned, yes, in previous slide, in general, n at the power of mu minus 1, where mu is the length of the impulse response. So in this particular case, it's 3 minus 1, so it's n squared. And n is the number of these symbols. So in this case, for pump 4 modulation, this is n equal to 4, plus 3, minus 3, plus 1, and minus 1. In this case, binary case, NRZ case, we had n equal to 2, yes, and here we have 4 power of 2, yes, so basically that's a 16 possible transitions. So I'm going to mark them now just to see how it goes. Yes, I'm going to use a green, for example. 1, so this is plus 3, plus 3, plus 3, minus 3, minus 3, plus 3, minus 1. No, wait a minute, plus, let's go from positive to negative. Minus 1, plus 3, minus 3. Then plus 1, plus 3, plus 1, plus 1, plus 1, minus 1, plus 1, minus 3, and so forth. I'm not going to draw all 16 of them. Yes, it will be sufficient for now. That what matters the most is that the number of possible transitions will also be only 4. From these 16 states, we can end up in any of the 4 states. So in this particular, but I do need to draw them all. Well, okay, I will draw them all. Plus 3, minus 1, plus 1. So I don't calculate the sum here. These are two symbols following each other, yes? So I separate them by comma, for example. And minus 1, minus 1, minus 1, minus 3, and minus 3 plus 3, minus 3 plus 1, minus 3 minus 1, minus 3 minus 3, yes? So I'm not going to give you in practical part here for that reason quadrature amplitude modulation, because it will just take so much more time for you to draw these plots, these trellis, and they have to be drawn manually. At least I don't know any program, any toolboxes in MATLAB or whatsoever that can help you in plotting this automatically, but you may search, maybe you will find something, and then will also tell me that, for example, MATLAB might have some toolbox that is capable of drawing these trellis diagrams for us. So let us consider this case that we start with the state plus 3, and we can send 4 possible symbols, either plus 3, and in that case we are going to end up in this state, either plus 1, and in that case we are going to end up in the state here, plus 1, plus 3, yes, minus 1. In that case, we are going to be in this state, and minus 3, which will be this state, right? So no other possible transitions are here. So we cannot go to here, to here, to here. And this knowledge is exactly what makes this Viterbi algorithm work and find the errors. Yes, so these are obviously, if this happens, this is an error, and this cannot happen. Yes, and Viterbi algorithms has this information and uses it to actually find the correct symbols. Yes, so that's how this equalization is working. It's non-linear process, meaning that we cannot really write any formula to explain this thing. This is iterative algorithm that operates step by step. Yes. And accordingly, for example, let's show how this data transmission can be represented in a form of such trellis diagrams. So basically, we need to construct in our practical exercise today 2 trellis diagrams, one for transmitted data and one for the detection process itself when the Viterbi algorithm finds the correct symbols. Yes, so the first step is quite simple and pretty straightforward. We display all the possible states. Yes, so I have also prepared already the form for my practical part. Here in practical part, you will see that we'll have more states. In this example, we only have two possible states because only one previous symbol matters, and it can be either +1 or -1. And here you can see that with red color, we have basically denoted previous state. Yes, so we are starting with second time interval. Yes, so here this is red color previous state, green color new state. Yes, so we go from +1 to -1, and in the process send symbol -0.5. Yes, so this is our transmitted actual value for this value -1 that has been input at the channel. So basically we can say that here is our channel, here we have value -1 in the input, here we have value -0.5 at the output, right? And in the trellis, this is marked with this transition. Yes, so as we go to next symbol, this -1 that has been previously here, yes, the transmitted symbol becomes the previous state for the next symbol, right? So now this -1 is the previous state, and the current transmitted symbol is also -1. So we go from -1 to -1, and during the process send value of 1.5, the sign mean or the sign of minus. Yes. So similarly, we go through this step by step. Yes. Here we go to +1. Next step we go to -1, +1, +1, +1, and -1. And here you have this path in the trellis diagram that shows our transmitted symbol. We can write all our transmitted symbol here as values on top of these lines. Yes. And these values on top of these lines are actually values that have been sent into the channel. Well, that are produced by the channel. Yes, so this is our data that we are going to receive and that we need to demodulate. Yes. Well, as I said earlier, in this particular case, it will not have errors if we try to demodulate it by once. But as you imagine, and as you already have seen in the practical exercise number 5, yes, for example, here, for such impulse response as here, directly trying to demodulate data produces a lot of errors. Yes, so we have to use the equalizer. Now, this is just a process of this. This blue should be marking like this. Yes, so I didn't really change in this slide. But okay, this shows how this data is being transmitted. Now we need to receive this data and equalize it. And these procedures are not really separatable. So this equalizing and detection happens at the same time. Yes, so let's see how this actually works so that we can, in the next part of our practical exercise, actually try and calculate that for our signal and our channel. Yes. Before we go further, I'd like to add that actually during the transmission also we have noise. So here you can see that because of the noise, this value has been changed and this value has been changed. Obviously, we have some small noise changing all of these values, but I wanted to make these slightly different values and not much of them to simplify the process of explaining this example. In our practical part, however, all of these values will have some noise. More or less, it will be defined randomly with SNR of 10 decibels, for example, but we'll see that later. For now, it was just a representation of signal. Yes, so here you can see our data sequence, -1, -1, +1, and so forth. Here you can see that it is shifted by one position. Yes. Here we also had +1 previously because our data started with +1. Yes. And basically shifted to here. Here we have the channel output data, and here we have channel output data with noise. So here is plus noise, yes. So this table is just to summarize what we have done so far. Yes, so now we have this signal, and basically what this doesn't really change much as we did here. So this is exactly the same thing as we did in practical exercise here when we applied channel, yes. And then we actually even add noise. So what matters the most and when Viterbi algorithm starts working is the next step. So when we try and start to make the decision what is received symbol, is it +1 or is it -1? And it will turn out that we will need some time to make this decision. It is impossible to take this decision at once. We need to observe the sequence of the symbols we have received. Exactly in the same way, by the way, as it was working here. Yes, in this iteration algorithm, for example, yes, when we needed this sliding window, yes, here, to accumulate actually 15 or 31 or 45 received symbols, and only then we were able to start and make some update to our equalizer coefficients, yes, or update to our autocorrelation matrix. So we needed to accumulate some symbols before we could go further. Similarly, it will work here as well for Viterbi algorithm. We will need to accumulate some symbols what we have received to actually detect anything. So, and the detection process itself will go as similar path. So we will try and find the similar path in our Trellis diagram. However, in this particular case, we will not know for certain which is correct direction. So we will have multiple possible directions and we will need to evaluate all of them. So we are back to this graph of states. By the way, I'm going to actually make this a small window for myself because we are going to need it now. And it will help us, yes, to have it. So, and we will need to check all the possible transitions. So what is said by this first point, by this first paragraph, is that what we are going to do is to actually find the difference between all the possible 4 paths in this particular case. So consider that we have received symbol row k, and we calculate this row k minus 1.5 squared, row k minus 0.5 squared, row k minus 0.5, so that gives us plus 0.5 squared, and finally row k plus 1.5 squared. Yes, and these are called weights. Yes, so we find the difference of what we have received and what it should have been. Yes, so because we can have noise, yes, this value may be different. However, if we don't have any noise, then we will receive one of these 4 values. Yes, and accordingly, one of these weights is going to be smaller than others. Yes, so for example, some values here, for example, 0, and so forth. So in that case, we might know that what we have received was actually 0.5. Now it will matter from which point we go and where do we get to. Yes, so we'll want to study these transitions. This actually might resemble you very closely our previous practical exercise when we calculated this error. Yes, as you can see here, we also calculated this difference and we calculated this square. Now, in our practical exercise, we didn't really have this square because we were calculating derivative. Yes, and once you calculate derivative, for example, of x squared, you get rid of this power and are left with double x and further derivative of this x function. Yes, That's exactly what happened here. Yes. So this derivative and in this function, yes, is exactly a reason why we use this error. Here you can see this error has been factored out and basically compensated this division by 2. So we can say that here we have beta divided by 2 multiplied by 2. This 2 is actually coming from this power of the error, and after derivative calculation, we are left with this error itself, yes? And furthermore, then we calculate derivative of what's inside this error, yes, equation. So this is actually very, very similar. Yes, here we also calculate the Euclidean metric. By the way, we can calculate different metrics. We could calculate this also as absolute value, yes, without square. Well, it can affect performance, but at the same time, this can simplify the calculations because you need to realize that we will have to calculate this as some fractional numbers, for example, 0.11. And if we need to calculate the square, this is going to be more compute intensive rather than simply calculate absolute value. So the metrics can be different, but we are going to use the most often used one, which is called Euclidean metric between received symbol and what symbol could be. We do calculate this metric for all possible transitions in this Trellis diagram. Then, considering the fact that we are going to calculate for each of these states two metrics, metric 1, metric 2, metric 3, and metric 4, which are called weights, yes, in this particular case, we are going to choose only smaller one of these two. For example, let us consider that W1 is smaller than W2. In that case, we are going to choose this metric, and we say that this path survives. Yes, this path survives, and this is accordingly discarded. Yes, we don't have this path. Accordingly, we do similar thing for the second, and consider here, for example, that W4 is smaller than W3. Then this path survives, and this is left. So in that case, of the two incoming paths, we choose to survive only one with the smallest metric. Yes, that's how exactly this algorithm will work. And furthermore, once we calculate the next step metric, this already existing metric will add up. So basically for the next step, we will have this metric plus new metric, and it will accumulate over the steps, yes? So that's how exactly this Viterbi algorithm iteratively will work, and I will try now demonstrate you this process for this simple example. And after that, in our practical part, we are going to make similar steps for the more complex example, consisting of 3 impulse response values and more states. And once we have taken care of all our data, then we will be able to read the data. You may notice that in this Trellis diagram, in this state diagram, I have used different colors for these paths. So there are red paths and there are blue paths. So red paths are the paths transmitting +1. So all the red paths are transmitting symbol +1. And the blue paths are transmitting symbol -1. So you can clearly see that this state that goes higher, yes, or stays at the same level, at least, yes, in this particular case, or if we compare, for example, yes, outcoming, wait, how to say it, outgoing, yes, transitions, one that is lower is -1, that is one that is higher is +1. So they are relative one to another, located, one is higher, one is lower. Yes, that one which is higher is +1, that one which is lower is -1. Yes, and accordingly, knowing this information, we will be able to convert this transition into actual symbol that has been transmitted. And this way we will receive our data. So that will be equalization and detection in the same process. Yes. So now let's see the example. Consider that we have our received data with two noisy values. Here is noisy value and here is noisy value. Yes. And what we want to do now is to actually find the correct symbols, +1, -1, +1, and so forth. What is our real data hidden in these symbols? Now, as I have previously noticed, we might read simply signs. Here we have -1, here we have -1, here we have -1, and so forth. However, you need to consider that first of all, we will have noise that may change situation, and also we might have intersymbol interference that will distort the symbols. Yes, so this might not always work. So we do as we discussed just in previous slides here, and calculate all the possible metrics for each of these possible transitions. So here we have 4 possible transitions. For this transition, we take value 1.5 and subtract this received symbol from this value, yes, and calculate the Euclidean metric. So for this transition, we have calculated the Euclidean metric of 4. Next transition is this transition, yes, and accordingly it has 0.5. Yes, it has 0.5, so we have minus 0.5 our data, and here we subtract this value. Yes, so basically it's here, square it, and find the metric. Next transition calculates the next metric, and according with this minus 0.5 value, so here we have minus 0.5, that gives us plus, yes, and we calculate this metric. And last transition here calculates this metric. So we have calculated 4 metrics for this received symbol minus 0.5 with all the possible metrics respective to the specific transition. So basically this transition had metric 1/2, this transition had minus 0.5, this transition had plus 0.5, and this had minus 1.5, yes? So we have calculated all these metrics, yes? And now we need to choose for each of these states of these two metrics the smaller one. So we choose here 1, which is smaller, and here we choose 0, which is smaller, yes? Accordingly, of these two paths incoming to this state, only the path with the smaller metric remains. So we can say that we erase these paths and are left only with these two paths. At this step, however, it's impossible to tell if our symbol is 1 or -1. If we try and read this data, then we will notice that this is -1 and this is +1. Yes, and well, we still can say that this metric is smaller, and hence the real symbol should be -1. Because this matrix is smaller, we will read the smallest metric path, and that's actually how it will work. Yes. However, as we go further, some paths will become extinct. Yes. So basically, not all of these paths will be continued in the future, and we will be left with one true path that will be used to read the data. So let's continue and receive the next symbol, -1.5. This will require us to do the same procedure. However, you may notice now that we need to consider, when calculating the weight, the actual initial weight. At this moment, we had initial weight 0 and 0, so nothing really mattered. Now, however, we need, when we calculate weight, to consider what was the weight of the previous state. So, for example, let's consider this transition. So this transition comes from the first state where we had weight of 1. So this 1 adds received symbol minus the expected value, yes, so new metric calculation, and they are added up together. So here we have 10. For the next step, when we calculate the next transition here, yes, we originate from the state with 0 metric, yes, so here we have 0 plus, similarly, the difference between what we have received and what we should have expected, yes, for this transition specifically. So we calculate in a similar manner remaining matrices, and again choose from two incoming paths only one which will accordingly uh, survive, yes, and the second one will be eradicated. So as you can see in this particular case, these two paths are eradicated, and in this way the path that was here will no longer be continued, yes. So this also becomes extinct, and we are left with only these possible combinations, right? So we can now for certain know that this is symbol, as it goes down, this is symbol -1, which is actually true. The first symbol was indeed -1. So as you can see, we already can start reading the data. Here, however, we are still uncertain what it is. We may again use this information about accumulated metric, about accumulated weight, but again, considering that we may have noise, this may be incorrect. Yes, we need to continue detection to again extinguish the remaining paths. So we receive next symbol, which is 1.5. Yes, -1, 1 and 2, I mean. And again, do the same thing. We calculate the metric depending on point which we originate from. So we originate from first state, so the metric is 4 plus this difference. For the next transition, we calculate from the second state where we had 0, so we calculate this metric, and so forth. Again, we choose of these two the smallest one, and this path is kept. Similarly, this path is extinguished, yes, so we already may read the second symbol, which is also -1. Yes, so -1, -1, and furthermore, it goes further, yes. So this process is then repeated. Here I already made some simplifications. I didn't calculate this entire metric in the brackets. Yes, as we will write a simple program to actually make this process faster. But you may observe now that we no longer have a 0 total metric. Yes, so we now have this 0.09, which is actually because of this noise. So this noise value did not match precisely any of these values. So the closest value was here, and the difference -1.5 was actually 0.03, which should be squared, yes, in accordance with metric calculation equation, and this produces 0.09. So this part will be forever further in this decoding process, and each noisy value will add up to this metric. Yes, so basically, if we don't have any noise, then the truth path will be marked with 0 weight. Yes, but since we have some noise, then we should just search for the path with smallest metric. So this process will continue. I'm not going intentionally to take each slide right now. Yes, because we will now delve into more details after a short break in practical exercise and make much more complicated case. This is just some example that the same procedure is repeated over and over again. And as we repeat it, we can see that some paths are extinguished, yes, and only true path remains that marks our data. So now we need to read our data from this path, yes, and for that, we are going to use this diagram of the states. And accordingly, we will read our data. So the first symbol is actually not this symbol, -1, but the state we start from. So you can see here that we started from the state +1. So not only this symbol produces our data, also the state we start from is our actually first symbol. If we have multiple symbols, this will be multiple first symbols. So our first symbol is +1. Then we read symbol which goes below, yes, according with this graph, it's -1. This one is lower symbol, -1, lower, -1, upper symbol, yes. So from this point, we have two outgoing paths, yes. Which one is upper one is +1, which one is lower one is -1. And similarly, it goes till the end. And this way we read data. Also here, actually, we weren't precisely certain that this is -1. However, considering that we have finished our data transmission and no more data will be coming, then we consider the smallest metric path, yes. And in this particular case, this is actually real data that matches the data that has been truly transmitted. Yes, so this is how this Viterbi detector algorithm is actually operating. Yes, and now we will make a short break of, let us say, 17 minutes because it will be demanding for our attention. Yes, so you need to take some good rest before we continue. So let's take 17 minutes before practical part, and then I will show you example, and we will write a simple program that will help us automate calculation of these weights. Yes, so after 17 minutes, we will continue. We will start the practical part with your questions if you have. So for now, you can go and have some rest, and let us continue in 10:50. Yes, and we'll start with some questions if you have any. So okay, thank you and see you after a short break.